Welcome to the NUPOC video study guide number 92. We're going to do another pulley problem now, and this one is going to be a dynamics problem. So we're going to have some acceleration going on in our pulley system here. And we're going to try to find the acceleration, well, not try, we're going to find the acceleration of each block. And this is actually quite an in-depth problem to go through. There's a lot of algebra, especially towards the end. So we're going to set it up. And then I'm going to skip over a lot of the algebra, and then I'll present the solution. And then if you have questions about specific algebra steps, then we can discuss in the comments below. So let's get started. So we have this system where this rope is anchored up here, and then it snakes through these two pulleys, and we have M2 here and M1 here. And so the whole system can move up and down. If M2 moves down, then this whole pulley with M1 attached to it will move up. And we're going to assume that M1 and M2 are different masses, right? And we're just going to have this system set up, and it's as if I would just release M2 or just let the system go, and just let's see the blocks, see how the blocks accelerate, see how the whole system accelerates, right? Okay, so since this is a dynamics problem, when we sum forces, we're going to set it equal to mass times acceleration, right? Instead of setting it equal to 0 like we do for statics. So let's take a look at M2, right? And by the way, we're of course assuming all the pulleys are massless and frictionless, and the string is inextensible and massless as well. So if we look at M2, right, we of course have M2G pulling down, and we have what I'm going to call, or what I've been calling for the last few pulley problems, Ft pulling up, which is the tension in the rope, right? And that is equal to, so again, let's sum forces in the y direction here, and let's draw our coordinate system, right? Y hat, x hat, z hat, so we don't get confused. So we can go ahead and say, if we want to assume that positive acceleration is in the upward direction, right, positive y hat, so we'll have Ft minus M2G. Instead of equals 0, it equals M2A2. That's the acceleration of block 2 times mass of block 2. Now let's do the same thing for M1. All right, so M1, and I'm going to do it for this whole system here, this whole M1 with the pulley and the connection between them. Okay, so otherwise we just have to analyze them separately, and let's just consolidate those steps, right? So we have this pulley, and we have M1, and so we have tension of the rope pulling up on both sides of the pulley, and of course we have M1G down, and we will write 2Ft, right, minus M1G equals, not 0, but M1A1, right, which is the acceleration of this whole pulley and mass subsystem right here. Okay, so these are our two equations. Now we have to figure out a way to relate A1 and A2, so we can go ahead and solve this equation. This is Ft right here. So we can solve this equation for Ft, and then we can go back and solve for exactly what the accelerations are in terms of g. So what we do to do that is we're going to divide, we're going to look at how this rope, how the different lengths, the different sections of this rope change excuse me, this, I'm going to draw this line right here, change length with respect to each other. We don't need this line here. So we have this length, I'm going to call that L1. We have this length, which I'm going to call L2. We have this length that wraps around half the pulley, that's L3. This length right here is L2 again, it's the same length, right? And then we have the length that wraps around this pulley here, that's L4, and then we have this length here, which is L5. And so the rate at which these masses move up and down is related to the rate that these lengths of line get longer or shorter. So that's how we're going to approach the analysis. So we know that the string is inextensible, so the total length, capital L, remains constant. So we can say that, I'm going to write it over here to save space, L equals constant equals L1 plus L2 plus L3 plus L4 plus L5, right? And now we can even consolidate some of these things because we know that L3, L1, and L4 are all constant. So all we have is this should be 2L2, right? Because we have two lengths of L2. So this will be 2L2 plus L5 plus, I'm going to call this LC, right, where LC equals L1 plus L3 plus L4, and that's a constant, right? So now we have the lengths of the string, the different lengths, and now we want to find out the velocity, how the lengths change over time, which is the velocity, will give us the velocity of the different masses. So we're going to go ahead and take this equation and we're going to differentiate it with respect to time. So we will get, of course, LC is going to go to 0. So if I take basically dl dt, right, equals 0, right, equals 2, I'm going to say L2 dot, right, plus L5 dot, right, and LC is going to equal 0. So we can say that L5 dot equals minus 2 L2 dot, right? And these are just the velocities of the different masses. So we can say also that that L5, I'm going to write it over here, I got to save a lot of space since this is a long problem. We may have to go into kind of split it into two parts. L2, right, L2 dot, right, if L2 is increasing, right, that means L2 dot is positive. That means that M1 is actually moving down, right? So this is going to be minus V2, right? Minus V1, because this is mass 1 here. Whereas L5 dot, if L5 also is getting longer, that's going to be minus V2, where mass 2 is moving down. All right, I'm going to pause here because I'm running out of memory on my camera, and I'm going to come back in just a second and we're going to pick up from where we left off. Okay, picking up where we left off, we had said that L2 dot, which is the time derivative of this distance here, L2, is equal to minus V1, right? That is to say, if L2, right, is shrinking, then the velocity of mass 1 is moving in the upward direction, right? And L5 dot, right, this distance here, is equal to minus V2. So as L5 gets bigger, right, that means V2 is moving down, or the velocity of V2 is negative. Or, excuse me, the velocity of mass 2 is negative, right? Okay, and we also know, let's see, where did we write it here? Oh, right here, that L5 dot is equal to minus 2 L2 dot, right? So that means, and I'll write this in velocities here, so we can actually just say that L5 is minus V2, right? And that equals minus 2 times L2 dot, which is minus V1, right? So we can just say that, let's move this negative sign to the other side, these two negative signs cancel, so we can say that V2 equals minus 2 V1. Okay, and if we look at the Pulley system, we can see how that makes sense, right? So if L5, right, gets a meter longer, right, that means we took a half meter out of each of these lines here, right? So this moved, M2 moved down a meter, M1 moved up half a meter. So if this one is moving down at a certain rate, this one is moving up at half that rate, right? And if M1 is moving down at a certain rate, M2 is moving up at twice that rate. So that's this relationship right here. Okay, so now all we have to do is take the derivative of this to find the accelerations. So I mean, that's pretty easy. That's just, I'm going to write it all the way over here, right? So we just have v2 dot, which is just dv2 dt, right, equals minus 2 can come out front, and then it's just dv1 dt, or just minus v1 dot. So we're just saying that a2 equals minus 2a1, right? So that's all we're saying. So what we can do is we can actually take this relationship, right, and sub it up into these two equations. So we already have a1 in this equation, right? So we can just sub for a2 here, we can sub in minus 2a1, and now we'll have two equations, right? We'll have two equations that are both in terms of a1 and ft, so we can solve for ft, right? So if I write that out, we would have ft, right, minus m2g equals m2 minus 2a1, right? And we have f2ft minus m1g equals m1a1. So we have two equations, two unknowns, so we can solve for ft and a1, and then we can say, then once we know a1, we can use this relationship again to solve for a2, then solve for a2, right? And so then we will have, these are essentially our three equations, right? This equation and then these two. So then we will have a1, a2, and ft. And so from here, it's all just the algebra of solving the equations. So I'm just going to write out what the final answer will be. And this is, assuming that M1 and M2 are not equal, we find that Ft, the tension force in the rope, is going to be 3M1 M2G, right, over 4 M2 plus M1, right? And you can check the units real quick. It should work out, right? We have F equals mass times acceleration. We have two mass units on the top, right? Basically mass squared, divide by mass on the bottom, and then we have an acceleration, so units check out. And then for the acceleration of 1, A1 is going to equal minus G times 3m1 over 8 m2 plus 2m1 minus 1/2, and a2 is going to equal G times 3m1 over 4 m2 plus m1 minus 1, right? And so you can just take these three equations and then solve for these three variables, ft, a1, and a2, and you can see that obviously a1 and a2 will be in different directions, so if mass 1 is moving down, mass 1 is moving up, and vice versa. And the direction that they move will depend on m1 and m2, right? So if m2 is much larger, that'll be the one moving down, m1 moves up. If m1 is much larger, it will be moving down, and m2 will be moving up. So thank you for watching, and as always, don't forget to hit the button down here to subscribe so you don't miss any of the upcoming videos.